Did you know? We have published an Etabs course with a complete 20-story building design. The course will include complete guide to Etabs, from basics to advanced level with a completion certificate. Check link in description of this video.
In this lecture, we will be continuing the design of the masonry structure. In part 1 of the masonry structure, we modeled the structure. Now we will be calculating the stresses in the walls. We have calculated the limits of the stresses, that is the compressive stress limit, shear stress limit, tensile stress limit, and the axial forces in the end members. Now we will be considering the forces that are coming in the walls. These tensile and shear stress limits were calculated using the code UBC 97. In a similar manner, if you are utilizing another code, you can calculate the limits in the walls as per your code requirements. I have calculated the limits as per UBC 97 in PSI, pounds per square inch. Now I'll be going to Etabs, and this is the structure which we modeled in the part 1 of this lecture. And now I'll be finding the values of the stresses. First of all, you need to know that which values to look into. So I have made the ASD stress envelope. The design combinations were formed an envelope in combination, and now I am looking at the minimum value because Etabs considered the negative sign, and minimum means I'll be looking at the compressive stresses. So for the maximum compressive stress, I am getting a value of 272 KSI, while the limit as calculated here is 99 KSI PSI. So we'll have to make the wall thick, but preferably I'll do other methods in order to reduce this stress in the walls. So I'm getting a high stress value at this edge. However, the average stress in the other part of the walls is not that high. As we can see, the blue color shows that the value is between 0.44 and 0.22 KSI. So I'll try to reduce the value at the concentrated points. The envelope at which I am checking the stresses was formed in the previous lecture, that is the part 1 of this video. You can see the link in description for the part 1 of this video in which we modeled this masonry structure. Okay, so now I'll try to minimize the stress values. Let's select the slab and turn off the visibility, because we are not checking the stresses in reinforced concrete structure as the slab was reinforced concrete. We are only interested to see the shell stresses in the walls, as the design of the walls or the masonry structure is considered by the stress limitations in the wall. Okay, since there were parts of the wall which were having concentrated forces or stresses, so I'll try to increase the number of reinforced edges in the wall. That is, try to increase the reinforcement in the wall, that is at the localized points. We defined a frame section similar to a column, but I'll rather say it as reinforced column, but it's actually not a column, it's a reinforced edge or a part of the wall that is reinforced. So I have defined that as column in Etabs and making the part of the wall reinforced. Similarly, I have drawn it in the model. Since the stresses were high in the wall, so I have induced these chunks of reinforced portions so that these stresses would be reducing in the walls overall. Now we'll have to also mesh the wall at the points where we have added these reinforced element. I am meshing the walls for a better force transfer and stress transfer mechanism. Similarly, I added the reinforced element there, so I had to mesh the wall. Now assign the supports once again as fixed base and click on run analysis. And after analysis, we'll be checking the stresses in the walls against the limitations of the code once again. Let's check on the envelope combination. So we are getting a stress of 242 or rather 352 psi, which is still a lot higher than our limit of the code. As discussed in the previous part of the lecture, I have not modeled the interior walls of the structure purposefully in order to show you that when we are using a masonry structure, which is primarily composed of the masonry as a lateral force resisting element and the force and the element to resist the gravitational load. So we have to model the structure completely. I'll be modeling the interior walls as well now, so that the stress transfer from the slab due to gravitational load is lower. I have divided the band beam at the column joints. And now let's see if the stress is reduced. So the stresses seem to be still high above the limit. Please note that we are checking the compressive stresses right now. The compressive stress limit is minus 99 or simply 99 psi. So I unlock the model and will add the interior walls, so that the stress will further be divided between the walls from the slab. Right now the slab is transferring all the load to the boundary walls. So I've divided the line segment into 5 segments, so that we'll be able to draw the opening inside the wall. Since it was a 10-foot line, I divided into 5 segments, so each segment is of 22 feet, as I needed a 2 feet distance from the top. So that's how I snapped there and make the mesh in the slab for the opening. Similarly, horizontally, for the horizontal dimension of the wall opening for the door, I did the same. I divided the lines. So I get a 3 feet distance horizontally. Actually, the node must be forming at the edge of the shell in order to split the shell. Similarly, for the other wall opening. Now we can select all the null lines which we used for the modeling and delete them. Now let's draw the lintel beams. I'm making sure that the beam is broken at the points where the slab is meshed, so that a proper force transfer mechanism is formed at the nodes. As Etabs work on finite element method, and the transfer of deformation and forces and displacements is all through nodes. So let's see whether modeling of interior wall reduce the stresses. Yes, it has reduced the stresses. Let's compare in terms of values. So we are having a minus 130 psi stress as maximum, and apparently the maximum stress value is coming over here. So we are getting a value of 130.39. We can try to reduce this value by changing the parameters we utilized. We can either increase the thickness of the wall or the strength of the stone masonry we are using, but let's stick to the thickness and the stone masonry properties. We'll discuss other methods of how to still pass the wall in the stress check. So I'll be adding more reinforced edges or the reinforced areas in the wall, and I'll further add the beams in the structure so that the stress is properly distributed on the beams and a transfer mechanism between beam and the reinforced edges is formed, rather than all the stresses being going to the walls alone. So I am trying to concentrate the stress from the slab to the wall, to the reinforced edges, rather than all going to the slab. So let's try if it makes a difference. and see the stress values. Yes, the stress is now reduced further. There are a few more things we'd like to do. We'd like to add the reinforced concrete edges here. That is the reinforced elements over here, as the stress in the back wall is high as compared to our limit of the code. So we're getting a high stress value in terms of compression over here. So I'd like to enter or add reinforced edges here. And similarly, I'd like to add more reinforced edges here. That's a reinforced portion of the wall, which we defined as a column. But it's not actually a column since it's a masonry structure, so it's a reinforced edge. We defined that reinforced edge in the part 1 of this masonry modeling structure tutorial. The link of the part 1 is given in description of this video. So I added a reinforced concrete edge so that the force transfer is further enhanced, and I'll try to concentrate it on the reinforced edges rather than going into the walls. Let's run and check the stresses again. I'll be going to grid number 3. And divide the slab here as we add the reinforced edge. The purpose of adding reinforced edge in the midway of these wall panels is to reduce the stress concentration in the walls, rather transfer them into these reinforced edges. So I'll be seeing if the limit is now met or not. The maximum stress is minus 94 psi, which is within the limit of the code. Now let's check the other stresses limitations. Now we'll be checking the So I'm checking the tension in the walls. So the tensile stress is also exceeding the limitations of the code. Mostly interior walls are facing a high tensile stress. We can control the tensile stresses in a similar manner we control the compressive stress. So right now I am noting in the report that we are getting up 78.75 tensile stress, and if the architect permits, I'll increase the thickness of the wall to 10 inches or maybe 12 inches. So I have noted that in the report, and that's how we will be completing the design until the tensile stresses limitations are met, which will easily be fulfilled by the thickness of the wall and adding more reinforced concrete edges as we added in the compression part. So I am checking the axial force limitation here in the reinforced concrete edges. The limitations are already prescribed by the code as 24,000 psi in the reinforcement. Lastly, I am checking the shear stress in the wall. So we are getting a higher shear stress. The limit is 23 psi. Most probably we'd like to change the material of the wall as we are using a very low strength material, that is 600 psi compressive strength. So our stress limitations will be automatically increased by the code formulation calculated. So I am adding a reinforced concrete edge here in order to reduce the shear stresses, and it's a big span for a masonry only. So I have added a reinforced concrete edge here, and similarly adding the lintel beam here, which I ignored in the previous modeling techniques. Let's match these frame elements and combine the column again. Assign the supports as fixed supports to the base of the elements, and then run the analysis again and check the shear stresses. Similarly, in a tension stress manner, we will be using a high thickness of the wall for passing the shear stress check as well, if the architect permits. So our wall is currently failing at 78.75 of axial tension and shear stress of 39.24. So we would rather like to increase the thickness and the strength of the wall material, that is the stone masonry. And once that is done, you can do it easily, that the stresses limitations will also increase and the stress values will reduce themselves. So the code check will automatically be passed. The main concept was delivered. Okay, so these are also some important requirements the structure must be complying with for the reinforced masonry structure as per ASC 716 code. You can utilize any other code for checking the requirements of the structural configuration. Okay, so we don't have a weak story as on the structure is only have one story. Similarly, we don't have a soft story as the structure has only one story. So we'll write not applicable. N is means not applicable. We don't have any vertical irregularities as the structure is only single story. Similarly, for the geometric irregularity, mass and torsion. We can check the torsion irregularity in the structure. Let's check it. We have already discussed in detail the torsion irregularity check on the same channel, but let's emphasize here if we are checking it for the earthquake, since torsion irregularity is checked for the earthquake. So the ratio is less than 1.2. It means no irregularity in x direction and no irregularity in y direction. Okay. C means compliant. Okay, so the symbol shown in the table depict the following. The building conforms to checklist conditions, we write C, and the building does not conform to the checklist condition, we write NC, and then we'll have to revise the configuration. And similarly, NA means not applicable to the structure. That is how we design the masonry structure in Etabs.